Okay, so we're back. We're working on exponential graphs. This is section 2.5. This video pretty much covers stuff that you can see in problems 3 through 20 of section 2.5. So if you're following along in your book. And what we want to know is, first off, what is an exponential function? And they're different from polynomials in that the variable is in the exponent and not in the base. So here's an example. Y equals 2 raised to the x power. The 2 is the base, the x is the exponent. Note that this is different from something like a polynomial where you have y equals x squared, where the variable is the base, the x, and then the squared is in the exponent. So y equals 2 to the x. What does the graph of this look like? So the one thing we can do is always point-by-point graphing for y equals 2 to the x. And so we say, what's x? And then we say, okay, well, what's y? Equal 2 to the x. And the usual deal is to just do a bunch of numbers centered around 0. That's usually a good way to figure out what the graph of something should look like. 2 to the 0, that's always 1. Anything to the 0 is 1. So 2 raised to the first power, that's also just the number itself. So 2 to the first is 2. 2 squared, this is 2 raised to the second power, that's 4. 2 cubed, that's 8. Now 2 to the minus 1, remember that 2 to the minus 1 is 1 over 2. Right, so that's 1/2. 2 to the minus 2, for example, right? The negative exponent means put it down in the denominator, so it's 1 over 2 squared, which is 1/4. And then we have a 1/8 in the bottom there. So, as your x's become more and more negative, you just cut it in half each time, a half, a fourth, an eighth. As your x's become more and more positive, you just double everything. So 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, etc. So what does the graph of this thing look like? Now we'll put in an x-axis, put in a pretty tall y-axis. So if x equals 0, y equals 1. If x equals 1, y equals 2, so there's 1. There's 2. If x equals 2, y equals 4, so there's 2, 3, 4. And if x equals 3, y equals 8. So if I go 1 unit to the right, I actually double the number of units I go up. So 1, 2, 3, 4, 5, 6, 7, 8. Right? So to the right side, it is climbing very quickly. To the left side, though, every time I go over 1 unit, I cut the height in half. So at minus 1, that's over here, I'm at a half. And at minus 2, I'm at a half of this height. So in there. And at minus 3, I'm at half of that. So minus 8. Minus, at 1/8. And so that comes down here. So this is what's called a horizontal asymptote. Out here to the left. Horizontal asymptote. Never gets to 0. Right? Never gets to the x-axis, but it comes very, very close. Right? So no matter what number you raise 2 to, right? 2 to the minus 3 is an eighth. 2 to the minus 10th, well, that would be 1 over 1024. But no matter what number you raise 2 to the x, it's never equal to 0. Okay? So what's the range of this thing? Well, the range is what y's you can actually get as out from the function as y values if you plug in an x value, right? So you pick a y value and you say, okay, well, does that go through the graph at some point? So 1, 2, 3. 3 is in the domain, is in the range. Minus 2 is not, because if you look at the graph at minus 2, the horizontal line at minus 2, it never touches the graph. 0 is not in the range either, right? Because if you look at the x-axis, the graph never gets to it. So the range here is y strictly greater than 0. Okay, so we can graph a similar thing if we say, let's look at y equals 3 to the x. And what we can do is change the color on my pen. We'll go to red. And we can construct a similar table for 3 to the x. Right? So x is minus 3, minus 2, minus 1, 0, 1, 2, 3. Put in a little line here, a little line here. Again, 3 is my base, x is my variable. 3 raised to the 0, that's 1. Anything raised to the 0 is 1. 3 raised to the 1, that's 3. 3 squared, right? If you plug in 2 for x, you get 9. 3 cubed, that's 3 times 9, that's 27. Going negative numbers, you get 1 over these things. So 3 to the minus 1, that's 1/3. 3 to the minus 2, well, that's 1 over 3 squared, so that's 1/9. And 3 to the minus 3, well, that's 1 over 3 cubed, so that's 1 over 27. So we'll see if we can tack this graph onto the graph we have for y equals 2 to the x. Y equals 3 to the x goes through the same point, but it grows a little bit faster. When x equals 1, 2 to the x is 2. When x equals 1, 3 to the x is 3. So that's already at 3 here. And then 3 squared, that's going to be 9. That's all the way up here. 3 cubed, that's 27. That's way off the top of my graph, somewhere way up that way. Going backwards for negative numbers, well, if x equals minus 1, then we get 1/3 versus 1/2. So it's actually going to be a little bit below there, a little bit below there, a little bit below there, except we're getting so close to the x-axis it's hard to tell. So 3 is bigger than 2, so y equals 3 to the x grows faster. It also dies off faster. But like y equals 2 to the x, range is strictly greater than 0, and it grows a little bit faster. So this red one is y equals 3 to the x. The blue one here is y equals 2 to the x. In between those two numbers is a really useful number. Let's see what other colors I have. We have green. Let's try green. So E is a number. It's 2.718281828 ... I had a professor in college who said, 1828, that's when Andrew Jackson was elected president, or the year he assumed the presidency. So it's 2.7 Andrew Jackson. I don't know why I remember that, but I do. So E is between 2 and 3, and so e to the x is a nice exponential function that's in between y equals 2 to the x and y equals 3 to the x. They all look the same. All exponential functions look pretty much the same. Let's go back to my blue. So all exponential functions look pretty much the same. So generic exponential graph. What are the important points of an exponential graph that we need to keep in mind? Well, they all go through 0, 1. Right? Because anything raised to the 0 is 1, so they all go through there. And then they're very steep here, and then they die down to a horizontal asymptote at y equals 0. Note that this distance is 1 unit. Right? The unscaled exponential function has got a tail that goes out to y equals 0, and then 1 unit up is where it crosses the y-axis. Okay, so generally that's what an exponential graph looks like. What about changing the base? What happens if you change the base a little bit? One thing that I did in those 3 examples, y equals 2 to the x, y equals e to the x, and y equals 3 to the x, is that the base was always bigger than 1. What about y equals, say, 1/2 to the x? What does that look like? Well, remember that 1/2 to the x, we can rewrite that. 1/2 quantity to the x, well, that's 1 over 2 to the x. 1 to the x, 1 to the anything is just 1, right? So technically the x gets distributed to the 1 and the 2, but 1 to the x is just 1. If I have 2 to the x in the bottom, that can be written as 2 to the minus x. So this is the same thing as y equals 2 to the minus x. So if we're looking at it 2 to the minus x, well, we can compare it with a graph of y equals 2 to the x. We'll put in our 2 to the x graph, just the same numbers that we had above, 1, 2, 3. and that was 1/8, 1/4, 1/2, 1, 2, 4, 8. So 2 to the minus x, what does that look like? Well, 2 to the minus x, if we plug in x equals minus 3, what do you get? You get 2 to the minus 3, that's 2 cubed. So actually, when x equals minus 3, 2 to the minus x, that will be 8, because you're plugging in, it's a 2 cubed. And then if x is minus 2, you get minus 2 in the exponent, that's 2 squared, so this is 4, and then this is 2. 2 to the 0, well, that's always just going to be 1. 2 to the minus 1, well, that's 1/2. 2 to the minus 2, if I plug in a 2 there, that'll give me a 1/4, and then a 1/8. So, what do these two graphs look like? Well, y equals 2 to the x. Let's see, 1, 2, 3. Oops, this one should be down a little bit, right? Because when x equals 1, y equals 2. When x equals 2, 1, 2, 3, 4. Y equals 4. And then 2 to the x, 1/4, 1/2, 1/4, 1/8. So y equals 2 to the x looks like that. What is y equals 2 to the minus x? Well, it's just this graph, but flipped over the y-axis, which we haven't really talked about. But if x is minus 3, 1, 2, well, 8 is off the top of the graph. So if x is minus 2, right, then we'll have a y of 4. If x is minus 1, we have a y of 2. When x is 0, we get 1, because they're both exponential graphs, and then it looks like that. So this is y equals 2 to the minus x, this is y equals 2 to the x. And so there's our graphs. Okay, so suppose we want to move graphs around. Well, we know how to do this because we've seen the, we did this with parabolas, we did this with square roots and stuff. So suppose we want to graph y equals, say, 2e to the x minus 2 plus 5. Right? X minus 2, that means it's moved right 2 units. The plus 5 is up 2 units. And it's scaled by 2. And when we're building these graphs, start with the right by 2 units, then by the scaling factor, and then by the up 2 units. So, start with your basic exponential graph, right, which looks like this. 1 unit from the place where it goes through the y-axis down to the height of the tail. Right 2 units means we just move it right 2 units. But it looks pretty much the same. So this is right 2 units. Now the scaling is scaling by 2, and what's that going to do? That's going to double this distance. So it'll keep the tail at the place where it is. But now, since we've moved right 2 units, we will be 2 units up instead of just 1 unit up from the tail. And the tail still comes back here, and it still grows very high there. And now we move it up 5 units. One, 2, 3, 4, 5, 6, 7. Let me actually give myself a little bit more space here. 2. And try and get my lines to be close to accurate, even though I'm freehanding everything. So we take this is already at a height of 2. We add 5 to it to move it up 7. So we're at 2. 1, 2, 3, 4, 5, 6, 7. The tail here is 2 units down and out to minus infinity. So we go down 1 unit, 2 unit. This is where the tail is going to be, and then it's just going to come over and go out that way. And so that is y equals 2e the x minus 2 plus 5. So same kind of thing, except now the scaling is between the tail of the graph and the place where it crosses the y-axis. And so if you just keep the relationship between the